Well, electron transport dissociation could be applied for protein sequencing. Proteins is the chain of amino acid. Many amino acid are connected in series to form a protein. The question is how to sequence the protein. Okay, the who first succeed in protein sequencing. Yeah, his name is Frederick Sanger, right? He first sequenced the protein insulin. Okay, but now it can be done rather, pretty much easily. Okay, with mass spectrometry. Okay, mass spectrometry is a principal tool for deducing the sequence of amino acids in a protein. Protein is digested into shorter chains by enzymatic cleavage. Let's say we have this short kind of a protein, right? There are how many amino acids here? This is one here, this part, and 2, 3, 4, 5, maybe this one. Yeah. This is let me see. Maybe 5. Yeah, 5 protein. Amino acid. Okay. Now, how do we get this sequence? Okay. First, using enzymes now cleave these the proteins into fragments. Okay. Individual chains are cleaved to make fragments of all possible lengths. Okay. Let's say if enzyme cleave here, yeah, you can cleave any position. Okay, yeah, and the cleavage forms a lot of fragments. And use high resolution mass spectrometry, yeah, to deduce which amino acids are in each fragment. Okay, and then use computer. Computer can use this information to reconstruct the sequence of amino acid. Okay, so electron transport dissociation is a selective way to cleave polypeptides into fragments in a mass spectrometer. Okay, here you see the C and Z. C means if you cleave here, C means positive charges are formed on the left hand side. Okay, if you cleave bond here and then this part, yeah, on the left hand side is charged. Okay, charges on the left fragment, and G means charges on the right fragment. Okay, and then there are many fragments. Okay, and then with the mass spectrometry, then we get the mass of each fragment and using computer. Yeah, and then this is like puzzle. Puzzle matching, right? And with obtained information, then the computer automatically find the correct sequence. Okay, in the case we can use mass spectrometry and electron transport dissociation. Yeah, dissociate these actually fragmentation is done by enzymes, right? And then electron transport dissociation, each fragment mass is detected by the mass spectrometer. Okay, and now let me introduce a very important technique called matrix assisted laser desorption ionization, in short MALD, right? This technique has been awarded a Nobel Prize in chemistry. One of the developers is Japanese, whose name is Tanaka Koichi. He graduated only, he obtained only a bachelor degree. He worked in Shimatsu. Shimatsu, that company. Shimatsu is very famous for developing chemical instruments, right? There, he had developed this technique, matrix assisted laser desorption ionization. Although he only had a bachelor degree, he developed this technique and he got a Nobel Prize in chemistry. Okay, and this technique is especially very useful for the measuring the mass of very high number. It can measure mass to charge ratio up to 10 to 6, 1 million. Okay, this high mass is not easy to detect, but with this technique, it's rather actually very easy to know the molecular mass. But detection method is usually time of flight. Okay, so we call it multi-top. Time of flight, TOF. Okay, the multi-top is the usual term. So the resolving power is 1000 to 10,000, and mass accuracy can be 0.005 to 0.05%. Actually, it is very accurate. Okay, and what's the principle? Okay, let's look at this figure here on this repeller. This is a plate made of stainless steel, right? And then this is the melted sample probe, and on top of this probe, you put your sample, your analyte, but not alone analyte, okay, but with a matrix here. Matrix is what? Matrix is anything except your analyte. In this case, is protein. Okay. Now, protein is in the matrix. Actually, matrix is much higher. Amount is much higher than your analyte. Okay, and then you use this laser pulse into this part, right? Since the laser pulse has a high energy, okay, this one matrix and your analyte now ionized, ionized the matrix with some charge transport to protein here. Okay, when you shine this sample, sample plus your matrix with laser pulse, right? And then this part is ionized, and energy is transferred, some charge is transferred to protein, and protein takes positive charge, but usually the bonds are not broken, right? So molecules are still there, and then since now it is vaporized and it expands here. This is a supersonic expansion of a matrix with entrained protein. Okay, here it contains a lot of proteins. Now it goes into the detector. Okay, time of flight mass spectrometer, and then the mass is detected. Okay, here this is result. This is protein molecular peak alpha lactalbumin. Okay, and this is beta lactalbumin, globulin B and beta lactoglobulin A. You see the molecular peaks are visible. This is casein peak, beta casein A1, this is A2, but here look at the mass number. Mass number is quite high, 14,000. This is more than 24, about 24,000. So mass number is quite high. But with this technique, you can know the molecular weight very accurately. Okay? This is quite well adapted for studying macromolecules like protein, right? And this mass spectrometry is being well developed now. New techniques are emerging, and then a new technique now can be operated in an open air. Okay, let me introduce several techniques. The first one is DART, direct analysis in real time. Okay, real time. A direct analysis in real-time source produces electronically excited helium or vibrationally excited nitrogen gas, which are directed at the surface of an object to be sampled in an open air. Yeah, this is important. In an open air, usually, to operate the mass spectrometer, you have to apply high vacuum, but this is operated in open air. Okay, here is a helium or nitrogen gas. This is a very inert gas introduced to this this part. Yeah, here they undergo glow discharge, and then here at the this tip at the end of this part. Now the gas with excited neutrals now goes to object. Yeah, this is now object. Yes, is sampled in an open air. Okay, and then this charged sample is entering the mass spectrometer. Okay, that way. This is start source. Okay. For example, helium is excited, yeah, and then it reacts with water, and then it takes one electron from water, and this water becomes cation, and it reacts with another water, and here is the hydrogen ion, and hydrogen ion reacts with the N water molecules, yeah, and becomes this one, and it reacts with what? Your sample, right? And then this one molecular ion, yeah, plus this hydrogen now enters this mass spectrometer. Okay, and then this is open air sampling, right? Sampling is done in air, and then this ionized species goes into the this mass spectrometer. Okay. And another technique is low temperature plasma. By plasma, we usually think the very high temperature, but this is done in open low temperature. Okay, and is low temperature plasma is created by passing helium, argon, or nitrogen or ambient air through glass tube. This is glass tube with a grounded wire at the center. This is you see glass tube, and then grounded electrode at the center. Okay, and this around this tube there is a copper sheet. Okay, and copper sheet is 3 kilovolts. This AC alternating voltage is applied. Okay, here. And inside here there is a low temperature plasma is formed. Okay, and then this low temperature plasma is applied to the sample, and then the sample surface, from the sample surface some ions are dissolved. Okay, now these ions go to the atmospheric inlet of a mass spectrometer. Okay, and this sample information is obtained. Okay, so you may think that this low temperature plasma may be very is dangerous, but actually it is not. Okay, excited species in the plasma ionized and dislodged molecules from a surface such as human skin, even human skin. This one plasma is applied to human skin. So there is no electrical shock to the surface under study. So don't worry. So last technique is desorption electrospray ionization, DESI. This is a micron-sized charged droplets created by electrospray of analyte-free solvents are directed into the surface of an object under study. Wow, what's that? Now here, this is electrosprayed. The solvent now. Let me see. Oh no, this solvent enters this one, and then here inside this part it is electrosprayed, and then this one now scanned over the surface, okay, and then this surface information is detected by what? A mass spectrometer, okay. Yeah, unlike ion on the surface here dissolves in the droplets, okay. Further bombardment knocks the droplet into the air towards the mass spectrometer inlet. You see here, this electrosprayed, this species now hit the surface, yeah, and then a species from the surface is dissolved, and then they are detected, okay. And then usually this probe is scanned over the surface, okay. This is very interesting result, okay? And now let's assume on this paper, on this surface, you wrote this number 1432 with, let me see, with which one? This one, okay. This ink, this is blue ink, okay, blue ink. Then with this ink you wrote, okay, this number, and then let's say this ink, another ink, this is also blue ink, but structure is different, and molecular molar mass is also different. This is molar mass, mass to charge ratio is 372, around that, but this one is mass to charge ratio is 484. This is higher, okay. And with this ink you simply wrote, let's assume you wrote this part. In other words, you wrote here this one, and then this I'm sorry, this one, let me say this part here, yeah, like that, and then it is 4 becomes 9, okay, and also this part here, okay, and 3 becomes 8, right? So with these two inks, actually the number looks like 1982, okay, you understand? But first, since you wrote this one, yeah, underneath is this one, and then you wrote this one here, then it looks like 1982 with one ink actually, but you used two inks here, right? This ink and this ink. This is optical image, yeah. With the optical image, yeah, optical microscope, you don't know, yeah, whether this actually 1982, this number is composed of two inks, okay. But with this desorption electrospray ionization, it is easy to differentiate, okay. How do you do that? And then using this one, this probe, now you scan over this this number, and then first you detect the molecular mass of 372.4, okay. And then what? Although all the this ink molecules are dissolved, you only detect this one, yeah, and then it gives this one only, right? Because this part, right, was made by this ink, yeah. But if you use if you detect molecular peak, the 484.5, and then this one is not detected, yeah. Only this part, yeah? This part is detected, and then if we overlap this image A and B, you can construct this one, yeah. This is same as the optical image, but with this mass spectrometry, yeah, with this desorption electrospray ionization method, yeah, although it seems only one written is with only one ink, but actually you can differentiate. Oh, it's made of two inks. Okay, isn't that wonderful, right? Okay, this is it, and this is the homework problems. Yeah, I selected these problems, and then you solve the problems and upload in the uh, eCampus. Okay, as I mentioned that the problem answer, the solution set is found in the internet. Okay,